All right, welcome to lecture 4. Today we are going to start the design process for a new structural element. Over the past couple of weeks, we've designed beams under bending and flexion. Today we're gonna design columns under axial load. So you started the design process for your building, you've designed some beams, and now you need to make some design decisions regarding columns. How would you design, let's say you're designing a canopy like this, or like a structure like this. The columns are like the vertical elements. How would you start the design? How would you, what's that? You want to design the foundation?
First.
Yes, 100% you have to design the foundations, but today we're talking about the design of the column. How do you design the column? Any thoughts?
Yes.
If you were hired to design this column, what would you do?
We want to find out what's the compression applied on it.
Yeah, the load on it. That's a great way to start. Just figure out how much is the load on it. How do you get the load on the column?
By the beam.
From
From
yeah,
the beam,
reactions from the beam, weight of the floor, weight of the roof, whatever the column is supporting, we'll calculate dead load, live load to get the load on the column. Excellent. Now you know how much is the force on the column. What do you do next? So your first step was to calculate the load on the column.
Just figure out what's the shear.
Shear.
Yes.
Which was
Sorry,
the
the bending
section?
moment. Sorry, the bending moment.
Bending moment, shear, internal forces. That's a great point. What are the main forces in columns?
Tension, compression, the bending moment, shear force, deflection.
Okay, these are the internal forces on a rigid element. Here is like the rule of thumb. Beams usually designed for bending and shear.
Compression.
Columns designed mainly for compression. Some columns will have compression and bending. And shear as well. Like if you introduce bending, then you have shear. So in an example like this, most probably this column has just axial load. And this is what we're gonna deal with today. Today we're gonna design columns under pure axial load. Next week, we will deal with a column that has axial and bending. So what would cause bending on a column? So axial load is the load on the column. So we would get that.
The shear force could cause.
What would induce shear force on a column? Column is like vertical and it's supporting vertical load.
Like any horizontal force. Like
Any horizontal force. I like that very much. So if you have a column like this that is supporting any horizontal load, that will introduce bending, right? So if you look at this example, this is an exterior column, outside column on the outside wall. It's still under construction, but these girts, these horizontal beams, will support walls or windows, and they will create a projected area for wind to pressurize the wall. The column will support them and will have bending kind of out of plane. So think of it this way: when you're designing a column, is the column supporting just vertical load or vertical load and horizontal load? If it's vertical load, follow the procedure we'll talk about today. If it's axial and bending, we'll talk about it next week. All right? So, how do you figure out the capacity of the column? How much axial force can this column support? What is the maximum force that this column can support?
Depending on the strength of the steel we're going to use.
Depends on the strength of the steel. Yes, you're right. If you use stronger steel, the column will be stronger.
The cross section of the column.
Yes, the cross section of the column. So if the steel is higher strength, you have higher capacity. If the cross section is bigger, you give bigger capacity as well. Any other thought? I'm curious if you can
Type.
think of, wait, what's that?
The type of the column.
What do you mean the type of the column?
Hollow, I-beam,
Yes.
I-column, or circular column. It depends on the.
Yes, this
the
is
shape of the
represented by the inertia, the moment of inertia of the beam. Yes, you're 100% right. Area, moment of inertia, and F yield. Can you think of any other thing that will control the strength, the capacity of the column? There is one main decisive factor in the capacity of column.
Simply span,
What's that?
the length that is not.
Yes, the length of the column. The length of the column will make or break the capacity of the column. Super tall and slender columns, they are weak and flimsy and they have small axial capacity. Short and stiff, they have very high axial capacity. Can you think of why tall columns are weaker or have less capacity? So why the taller the column, the smaller the capacity of the column?
And
So-
because of its density.
Because of what?
Density.
Density of the column?
Is it something related to the
Self-weight?
Is it something related to the surface area of the column from the top and the
Surface
length?
area. Well, surface, yes, it has to do with the dimensions. It has to do with the dimensions. So if two columns the same height, if one is more stiffer, it is still stronger. I'm talking about a tall column and a short column. Why the tall, like everything the same cross section, why the tall column is weaker?
It's a different
yes, I
ratio
know.
between the cross section of the column and the length of the column. It should be like a ratio that stands for the length and the cross section to be.
Yes, this ratio actually is very important. This is the ratio that governs the design.
Because of the moment, because the
Moment.
is distance multiplied by the load, so the load is. still the
Let's
same.
say the column has just axial load. I'm just curious if you can find why the taller the column, the smaller the capacity.
الفرص اللي جاية من الجنب
Okay, what about it?
ممكن الهواء مثلا يزق البلدن.
Yes, you're 100% right. But let's consider a column with just axial load. No bending, no horizontal force.
أيوة عشان هي برضه شايلة نفسها.
Because of the self-weight, because it's taller. Okay, this is a mode of failure that is governed by the height.
Because of the buckling. Yeah.
The buckling, yes. What is the buckling?
Rotation, like rotation.
Okay,
Torsion, like
the
torsion.
buckling is a phenomenon only presented in members under compression. A member under compression, if it's too long, it could buckle. It could deflect like that. So even though the material has not reached its strength, because of the length of the column, the member could buckle. The column could buckle. And these are the two steps we need to do in order to design columns. We're gonna check if the stress, if it's short, we'll check that the stress under axial load does not exceed yield. If the column is too long, we'll check that it's not gonna buckle. So we're gonna do these two checks. Check the stresses below yield, check the buckling capacity.
So,
Yeah.
about the yield, it depends on the class of the of the steel, right?
Yes.
So why, if it's like really long and still within the resistance of the column, why should it buckle? Like I mean, if the resistance of the load
Yeah.
is still bigger than the load applied,
Yes.
so why should it buckle?
That's a good question. Let me show you why. So here is what I mean by buckling. If you have a member in compression, you could reach yield, you can crush that element, or it could buckle. So how do we get the load that will cause the axial column to buckle? We can do that from the equations we got in structure analysis. In structure analysis, we established that the bending moment or the deflection is the double integration of the moment. So The moment at any point is the axial load multiplied by the distance y, and the double integration of the deflection, like the sideway deflection, is the bending moment. So we can solve that equation to get the critical axial force that will cause buckling. And this is the formula. It's called the Euler load. The Euler load is the critical load above which the column will buckle. So if your axial load is less than the Euler load, it's not going to buckle, it's going to carry the load. If it's higher than this number, it's going to buckle. So let's take a closer look. What does it depend on? Pi, that's a constant. E is the modulus of elasticity for steel. So given the steel grade, it's constant. You're left with mainly two things: the moment of inertia of the cross section and the length squared. It's not just like linear with the length, it's like the length squared. So if you increase the length by a little bit, you kind of square the effect of buckling. So columns are very sensitive to their height. All right, so if you plot this equation with the factor lambda. So lambda represents the only variable in the critical load. It's the ratio between the effective length and the radius of gyration, which is a way to translate the load into stress. So what is the difference between the critical load and the critical stress? What is the difference between the load and stress? Force and stress. Force is in kilonewton. Stress is force divided by area. So if you divide the critical force by an area, it gives you the critical stress. If your column is stressed more than this number, it will buckle. So it kind of takes the shape out of the equation. It's going to divide by the area, so you can calculate the stress and compare it to the critical stress. From this expression, you realize that it's very helpful, it's very beneficial to use the cylinderness ratio lambda. Cylinderness ratio lambda, it depends on the effective length divided by I or R. Some codes will say it's I, some will say it's R. It's the radius of gyration. What it is, it's the moment of inertia of the cross section divided by the area under the square root. All right? So lambda is the ratio between the length or the height of the column and its stiffness, how strong it is. The taller the column, the bigger lambda is. So this is a relationship between lambda or cylinderness factor.
What does cylinderness mean?
Cylinderness means is the column stiff or is it small and cylinder and flimsy? So a stiff column is usually big in dimension, short in height. So that's a very stiff column.
The ratio between the length and the dimension.
It's the ratio between the length and the ratio between inertia and area. So the radius of gyration is just the square root of the moment of inertia divided by the area. It only depends on the dimensions of the cross section. So you can say that lambda is the ratio between the length and the dimensions of the cross section. The bigger lambda is, the smaller the critical load is. So if your column is longer, very long, the critical load becomes smaller. So it can support less capacity. This curve is very important. The code actually uses it to define buckling. It's called buckling curves. In a perfect scenario, you can load the column all the way till the yield stress. You can keep on compressing the column until the fibers of steel yield. That's the maximum stress you can achieve. If your lambda is shorter than a certain limit, which is lambda 1, you can get it from this formula. Modulus of elasticity is constant. Yield stress depends on the grade. So if you know the stress of steel you use, you can get lambda 1. At this line, if your slenderness ratio is smaller than that, the column is probably short and stiff, and it will fail under yield compressive stress. If you calculate your length of the column divided by the geometry, and it's bigger than this line, now your column will buckle. And it will buckle according to this curve. So it's like a telltale curve if your column is going to buckle or going to fail under compression. The shorter it is, it's more likely to fail under compression. The longer it is, you significantly reduce the axial capacity all the way to, like, theoretically, the column just can't take its own weight. Like, it's just so tall, under its own weight, it will just buckle. And this would be like in a case where you're transporting a steel member. Maybe you don't want to support it vertically. Maybe you kind of want to support it horizontally because it's so slender, it cannot support its own weight. All right, so this is like perfect case scenario in virtual world. In real life, things are not as perfect as this curve. Do you have a question?
Yes, I don't get the difference. I got confused between the lambda 1 and the lambda.
Yeah, lambda 1 is just the limit between the cap, the straight part of the curve, and the curved part of the curve. Anything less than lambda 1, this is failure under compressive yield. Maximum stress you can achieve in the column. Anything right to lambda 1, buckling will have an effect.
Okay.
Does that make sense?
Yes.
All right. So what is that red and these dotted lines? These dotted lines are like experimental results. Let's take a section, like a column, and go and test it in the lab and see what's the maximum capacity. So when the column had like a slenderness ratio, let's say like more than 1 over here, it resulted in like that dot. Failure load was over here. A shorter column, the failure load was over there. So my question to you is, why the actual experimental results are lower or less than the theoretical perfect equations from the Euler load? Why there is a difference between reality, real columns, and the equations from like the theoretical pure mathematics?
Because different loads.
On the theory.
Well, according to the same load, theory gives a different number than actual testing in the lab.
Do we take into consideration the live load?
Well, let's consider like a fixed load.
It's a fixed load. It's not
Under the
moving,
same
it's
load.
The same load. Okay.
So under the same load, theoretical, mathematical equations gives different results than actual tests in the lab.
Not maybe because
What is the difference between virtual theory equations and real life?
the angle is
I like that very much. That's a very good thought. Any other thoughts?
maybe the
What?
angle isn't 90 degrees versus
Yeah.
90 degrees.
Maybe reality is not perfect. That's exactly it. It's called imperfection factor. Because the column that comes out of the factory, it's not like 100%, 99.9% straight. You could have like a dent. When you load it, you're not loading it like perfectly in center. It could be like a millimeter off. It could be like within certain tolerances. So the reality is actual life is different from theoretical, just perfect circumstances where the load is perfectly in the center, the column is perfectly straight, and there is no imperfections whatsoever. So the code will introduce something called the imperfection factor. The imperfection factor will create more than one curve that represent the red curve. The critical axial load that will result in buckling depends on only two things: the length of the column and the geometry of the cross section. So which length of the column do we use? We use something called the effective length, not its actual length, the effective length. So what is the effective length? The effective length, it depends on something called the effective length factor. The effective length factor will take into account the types of support, if the support is fixed or pinned. The reason why, if the support is fixed, the deformed shape is different from a support that is pinned. So the most typical, most simple axial column loaded is pin at the top, pin at the bottom. In this case, the effective length factor is 1. So its actual length is the effective length. So you can always start there. Is the column pin at the top, pin at the bottom? If it is pin at the top, pin at the bottom, then the effective length is the actual length. And in the example, or when you're designing a structure, you go look at the actual length of the column, you multiply it by 1, and that's your effective length. So let's say you're designing this building that we're in right now. How do you get the effective length of like the column at the corner of the room over there?
How do I know that it's pin or pin fixed?
So you're the designer. You are the designer. How do you design a column that is pin at top or fixed at top?
I don't get it.
What's that?
I didn't get it.
You don't get it?
Yes.
How do you? So you are the structural engineer that designed the connections. Yes. So how do you design a connection to be pin or fixed?
Maybe the balls with the red ring.
We did that yesterday.
The balls and welding.
Yes, for structure analysis when we were talking about rigid connections. Rigid connections, they are designed to be fixed. Pin connections are designed to be pinned. So you actually have to design the connection. So you know your assumption. I designed it with few bolts, it's pinned. So that's step number 1. You know if it's fixed or pinned. How do you get the effective length of a column in a building like this?
I consider the height of each floor.
Yes, yes. How do you get the height of each floor?
Architecture design.
From the architecture drawing. So you pick up the phone, call the architect. What are the floor-to-floor height for your building? They will tell you, we want 3 meters, we want 4 meters. That is the actual height, and then you take into account the effective length factor.
So I didn't get the actual height.
The actual height you would consider floor to floor.
Means from slab to slab.
So you will have to look at the connection. Where is the connection between the column and the beam? I would take it from beam to beam.
Okay, I'm talking about like concrete building.
Yeah.
It's fixed support, right?
It depends on the reinforcement detailing. If the reinforcement is developed in the wall or in the column, it is fixed. It could be designed otherwise. So here's what I want to say. There is another very important factor before we spend too much time on this. Your column, the column of a, the height of a column in a building like this could be braced by another beam at mid-height or along its length. It would be something like this. Do you see how this column, even though from point A to point C it's 6 meters, there are side beams framing into it? These beams will prevent buckling. So it will buckle between those beams. It will buckle between C and B and between B and A. So the buckling or the effective length is the length between the points of lateral bracing. Okay? So now we're getting very close to what I expect you to do when you design a column. First, figure out the actual length of the column. Second question, is there any beams framing into the column that will change the effective height, the effective length? To make things more interesting, you can have the beams that are going in the x direction with no beams in the z or y direction. That means it has a buckling length in x different than buckling length in y. Does that make sense?
Yes.
You need to pay attention to this. So what the difference this will make is if there is no side beam, the effective length is the entire length. If there is a side beam, the effective length becomes the distance between the beam at the top, the beam at the bottom. So when we go through the code equations, the code will say use the effective length of the column. Where do we get the effective length?
So the effective length is the height between a beam and a beam. It's not from the base of the column till the floor.
Okay, so let me share with you a very important piece of information. The effective height about a cross section could be different in one direction than the other. So let's say the cross section has like an I shape. The strong axis, let's call it Y, and the weak axis could be Z. If the column wants to buckle about Y, you use the effective length in the Y direction. If it wants to buckle about Z, use the effective height or length about Z.
Okay.
So what if there was like a beam in this direction, bracing the column this way?
So it's from the bottom till the
To
Y.
that beam.
To that beam. But if I took it about Z, so it's from the bottom till the top.
No, that's the thing. That's the thing. Is this column braced about Z or about Y? So this is the I, this is Y, this is Z, this is the axial, the longitudinal direction of the column. And now there are beams framing in this direction.
Okay.
So, is this beam braced when it buckles about Z, or is it braced when it buckles about Y?
It will buckle on Z, from the direction of Z.
It could buckle about both. It could
Yes.
buckle about Z or about Y.
Yes.
So
But
this beam is bracing the buckling about Z or about Y?
about what?
No, about Y, it will deflect like this. It's little bit, it needs like a little bit kind of imagination, or you need to visualize in order to understand this. It's very important. If nothing is bracing the beam, the column, it will buckle the full length. If there are side beams, it will buckle between the beams.
Like that cross, okay?
Yeah.
If we cancel, it's not crossed anymore, okay?
Yeah.
It's only from one side. So
Yes.
it's at the x direction. Let's
Yeah,
say that
so
this
let's-
is the x direction.
So
this
let's
is
say
the z direction.
here, it's braced here,
But,
in this direction.
but there are no beams on the other side.
Yes,
right?
like this one.
Okay. So the effective length, if I'm taking it from that side, the side that has no beams,
Yeah.
so it's from the bottom till the top.
So let me say this.
Okay.
In this case, the buckling about Z, effective length about Z is the actual length divided by 2. If
Okay.
that was
At the half.
Yeah.
Okay, at the center. Okay.
L divided by 2. Because you put your finger in Z and your other fingers are showing you the buckling about Z.
Yes, about
And
Y will
about
be
Y,
L.
the effective length
It will be
about
L.
Y is the full
And-
length.
Okay. Yes.
Super important to get this, all right? And then you add to it these factors. If it's fixed at the bottom, fixed at the top, you multiply the actual length by 0.7. So it shortens it a little bit. If it's fixed on one side and pinned on the other side, use 0.85. All right. So these are the 2 checks that the code will tell us to do. Let's use the Eurocode 3 as an application for this design exercise. If the column is tall, most probably this is not going to govern. This capacity usually gives you like a big capacity. If the column is tall, you need to check for buckling. If the column is very short, then that will govern the design. All what this is, make sure that the area of the cross section multiplied by F yield divided by this safety factor, which is 1, that becomes the capacity. Your capacity needs to be bigger than the factored load, as we did before. So this step, just first check if the column is short and stiff. If the column is tall, you need to consider the buckling resistance for the column or the member. So this is the Eurocode 3. This is section 6.3. These are the exact equations of the code. It tells us to account for buckling. This equation is very similar to the equation before, but it has this factor. This is a reduction factor that comes from the buckling curves. The buckling curves are smaller than the theoretical behavior, and we talked about why. Because actual life is not perfect. And the table above gives you the imperfection factor. So each shape, depending on the geometry of the cross section, you can pick the buckling curve. There are buckling curves from A to D. This is buckling curve A, B, C, D. And as you go deeper, this is a reduction in the capacity. So these factors will reduce the capacity. If the reduction factor was like 0.9, something here, you take 90% of the stress on the column. If the reduction factor is like 0.2, you take only 20% of the capacity. So you slash down the capacity. You could be using a lot of steel, but because your column is so long, you can just like use a fraction of what the yield stress of the column is. All right, so how do we get these numbers? What do we need to get the imperfection curve? How do we choose the imperfection curve? Well, it depends on what shape you design your column to be. And let me say this, I like hollow sections and closed sections for column. They're very effective because they don't have lateral torsion buckling. They don't buckle as easily. Open sections like these, they're generally, you need to check them more closely. Open webs like these, you will have further reductions in the capacity. So when you're designing a light beam, there isn't a big load on it. It's mainly flexure. It's braced on the top. Maybe you can resort to these light sections. When you're developing a column, maybe you want to do a closed section. The I sections works as well. You just need to follow the equations to make sure that you have the correct buckling capacity. All right, so where do we start? We start by choosing a section, and then depending on the height compared to the width, you see which buckling curve do we use. And from the buckling curve, we get the imperfection factor. So we will go to, depending on the cross section, you go to the section you chose, you figure out about the direction you're calculating, what is the buckling curve, and then you go back and get the imperfection factor of it. And from there, you have all what you need to calculate the reduction factor. This is the reduction factor that will reduce the capacity of the column. It depends mainly on lambda, or the cylinderness ratio, and alpha, which is the imperfection factor. That's pretty much it. Yes?
I did not get how to calculate the imperfection factor.
The imperfection factor, you first choose a section of the column. Do you
Okay.
want to choose a column box or I section? So let's say we considered an I section. Then you compare the depth compared to the width of the section. If it's more than 1.2, you check the thickness of the flange. Let's say the thickness of the flange is less than 40, then above the y-axis, you use curve A, above the z-axis, you use curve B.
Curve B.
Does that make sense?
Okay.
So if you're going to use curve A, you go to the imperfection factor buckling curve and use this number, 0.21.
Okay, why do we need that graph?
Why do we need the imperfection factor?
The graph, the reduction factor against the non-dimensional standard.
Yes, because this
Well,
is
they-
how you get the reduction factor. This is how, like, you use the non-dimensional slenderness,
Okay.
and you hit the curve, the buckling curve, according to your imperfection
Okay.
factor, and then get the reduction factor.
Okay.
But you can calculate it. You can calculate it from this equation. This equation pretty much will tell you what is the reduction factor. Okay? I want to share with you a very interesting check. If your slenderness ratio, lambda, is less than 0.2, most probably there is no buckling. Like, you don't have to check for buckling. It's just going to be the axial strength according to the material. It's going to be like check 1 will govern. Which means that your column is very short and it's very stiff. Okay. Here is an interesting check. If you don't use a section that looks like a cross like this, or an open channel, you don't have to get here. But let's say you're designing an element that needs to have a certain shape like this. That will introduce something called torsional or torsional flexure buckling. It introduced additional shapes of buckling. It could buckle in flexure and warp. It kind of complicates things. So the code, luckily, gave us a way to design it. Like, think of, we need to figure out this on our own. That would be very challenging. So it's a good thing that the code gives us methods to design different types of sections. Having said that, you're the designer. If you choose an I section, just use the equations for the flexure buckling. Now, I think we're ready for an example. Let's say you're designing this building and you're designing the column over there. First step, get the load. How do you get the load? You start with the framing plan. Do you remember, like, the structural layout? Step number 1 in designing any structure, figure out where the columns are, where the beams are, and then by the tributary area, you can get the load on the column. So this question is asking us to design the column at grid line E and 3.
Sir, is this top view or side view? This side view, right?
This is the plan. This is top view. This is the plan. These are like the slabs, and these are beams. This is an elevation. This is like the column. So you have some geometry. You know where the axes are. So this is grid line E, this is grid line 3. So the design of this column, let's get the information from the design. The length of the column from the architecture design, it's 4.335. Yeah, why would they do that? Why would they choose that exact height? Because they need to fit the lighting and the ceiling and the finishes. So we kind of add everything together. The thickness of the tile is that much. The thickness of the mortar or like the topping is that much. And then you figure out, you know what, I need that number. So you need to accommodate your clients. You're like, fine, you need this, I'll design it for you. So that's the height. And let's use a steel in the steel grade S355. Let's start the design by an HE section. It's an I section. 340, that's the depth of the section. Let's see how we design a column from this section to resist the loads on that column. So what are the factored columns, like the design load on that column? You get the self-weight, you get the dead load, you get the live load. You use the factors, 1.35 dead, 1.5 live, and then you figure out the axial load. That's the axial load. 3326 kilonewtons. So it is supporting a lot of load acting on it. It's probably because it's a multi-story building, so the load will accumulate. The columns at the bottom will have a lot of load. The column at the very top is just supporting one level. So you don't have to use the same section for the entire building. Every so often, every so many floors, you can reduce the section a little bit to be more economic. So, where do you get the properties of this section? We know that we need areas. Okay, it's not the code. It's like, what's that?
There is a table.
For each section.
Yes, these are commercially available sections. You go to a steel fabricator and they will give you a list of available sections. So the fabricator will issue catalogs with the dimensions of the different sections. So this is the section we chose. It's HEB340. It would tell us the height, the width, the second moment of area of the moment of inertia, about Y and about Z. Y is the strong direction, Z is the weaker direction, and it will tell us the radius of gyration. This is I or R. So a lot of the information we can get just from the properties of the cross section. All right, so here is the summary of the cross section. That's the area, the width, the height, the thickness of the flange. We got that from the commercial tables. Let's check the assumption. Let's assume it's class 1. So we'll go into the code table under pure or axial compression, parts subject to compression, and make sure that the ratio C over T is less than this magnitude. If it's less, that means it's class 1. So let's check the flange and then the web. This is the flange, this is the web. And after doing this, this is what we did in first week.
Yes.
Section classification. We'll figure out that it is class 1. So in pure compression, the section is class 1. This is a good sign. We will use the code equations for class 1. If it turned out to be class 3, you use the equations for class 3, which means that class 3 is flimsy. It's going to be weaker. Section class 1 and class 2, they're much stronger and they can take much load. All right. Here is the first check. The cross-section verification. According to the axial load, how much the maximum capacity the section can support. This check doesn't take into account buckling. So we have to account for the second check, which considers buckling. So what we need is the following. We need the unsupported length about Y and about Z.
It's the same, right?
So because it's pinned at the top, pinned at the bottom, no beams framing into it, it happened to be the same. And then we're going to figure out the slenderness ratio. It only depends on the radius of gyration and the effective length. So we do that always for buckling. You do about both directions, because the column could be strong in one direction but much weaker in the other direction. So you check both, and the governing will be the smaller capacity. So you check both directions, and the capacity depends on the weaker direction. All right, so what I did here, I got the slenderness ratio, and then you need to get the curves based on the width and depth of the cross section in order to get the imperfection factor and choose which buckling curve. When we go through all of these steps, we are ready to calculate the reduction factor. So I'm going to use the non-dimensional slenderness ratio and hit the buckling curve depending on the geometry of the cross section and get the reduction factor, which is something we can actually calculate from the equation. Once we get the reduction factor, you just substitute in the code equation and reduce the yield strength by the reduction factor, and that will give us the capacity considering buckling. So this one here is 4,000 kilonewton, and the yield one was 6,000. So do you see now how the buckling reduces? Buckling will always reduce the capacity. But what was the actual factored load? It was 3,000, right? So what I always like to do is check the ratio between the demand and the capacity. How much load is on the column divided by the capacity of the column. Yeah, you don't want it to be more than 1. You don't want the capacity is bigger than, or the demand, the force, bigger than the capacity. You want it less than 1. So what would be a reasonable ratio?
0.5.
Do you want, like, you're using only half the capacity, 0.5?
Sustainable, but
0.8,
it's really safe.
0.8, 0.9.
0.8, 0.9, 0.9, like you're very efficient, like you're pushing the limit. You're designing to 90% capacity.
What if the people living in the building like made a party or something, so the load would be extremely.
That's a great discussion. That's a great discussion. What if something happens?
Safety measure. Yeah, we take the safety by multiplied by the factor, but still, what if they are like bad people? So the.
Okay, you're on the right path. But are you suggesting that you put extra factor of safety on top of the equation factor of safety, the code factor of safety?
No, by just making it like safe for me and for the future. Maybe like we our family, like I have a little sister, so
Yeah.
she wants a swimming pool.
Yeah.
So like, okay, mama, let's go and get a swimming pool. And it's, of course it's not right. Maybe
It's not designed properly?
Yes.
Okay. The reason why I like this discussion very much, because the client, when you discuss with anyone you're working for, they don't like this to be like 0.5 or like 0.4. This is a waste of material. This is going to be very expensive.
That's true.
So they like to see like, you know, north of like 0.8. The question is, how far do you go? Do you want it to be 1?
No.
Why? 1 is most economic. Do you want to have a design for 1?
No.
You'll feel uncomfortable? It's too
1.8
close to the edge?
1.79
Is good?
Yes.
Okay, I personally don't like to go above 0.9 because I need to leave some room for the design of the connections. If you design the member for like 100% capacity, the connection might become very expensive. It might become like you can't actually fit enough bolts and welds to support that member. You know what I'm saying? Because like you're using a small member with very big load on it, the connections might get in the way. So even that, like because the depth is not very big, so you have just limited dimension to length to weld. So what I want to say is 0.9 is reasonable, and you can argue with your clients that if you push it north more than 0.9, the connections are going to become challenging. So you're going to think ahead and leave some room for the design of the connections. All right, so that's pretty much it, what I wanted to talk about. I have one more example for you. You can go through it. It's pretty much the same process. So in order for this to make sense to you, just make sure that you cover the answers and you see if you can get the actual.
Can we take a break first?
What's that?
Can we take breakfast first?
Yes, we'll take a break and we'll do like examples. And I also want to show you the equation for the Egyptian code. This is something that will be released later, like with an example on the Egyptian code. But let's first take a break, and then we will continue the discussion afterwards. All right? If you have any questions, come see me. If not, see you in the tutorial. See ya.